Our mission today is a really rapid and thorough deep dive into periodicity. We're going to focus specifically on period 3 of the periodic table, so that's sodium all the way across to argon.
Right.
If you need a shortcut to understanding how structure and bonding just change so drastically across one row, this is it. We're
Yeah.
going to distill all the key facts, the trends, and I think most importantly, the core reasons why they behave the way they do.
And that why is really the heart of periodicity, isn't it?
Mm.
It's all about the recurrence of patterns.
Exactly.
We know now it's all based on atomic structure.
Yeah.
But I think it's amazing to remember that pioneers like Mendeleev used these exact patterns to predict elements that hadn't even been discovered.
Like germanium.
Exactly, germanium, long before anyone even knew what an electron was.
Mm-hmm.
His foresight just proved there was this deep, predictable order to everything.
Absolutely. And we're going to use that order to connect the dots today. So our roadmap is pretty clear. We're starting with the physical trends. Things like size, melting points, ionization energy.
Mm-hmm.
All directly tied to electron configuration. Then we're going to pivot hard to the chemical behavior. We'll look at oxidation states and the really crucial acid-base nature of their oxides and how their chlorides react with water.
The whole story of period 3 is just a story of changing bonding.
It is. Okay, so to start with the basics, we're in the third row, period 3. Every element here is adding electrons into that third principal quantum shell. But the very first trend we hit, atomic radius, feels a bit, well, counterintuitive.
It does.
The atom actually gets smaller as you go from sodium to chlorine.
Yeah, and this is a fantastic illustration of the tug of war that's happening inside the atom. As you move across the period, the inner electrons, the ones doing the shielding, that effect stays roughly constant.
Because you're in the same energy level.
Exactly, you're in the same period. But the nuclear charge, which is just the number of positive protons, that increases steadily with every step you take to the right.
Okay, so you've got this constantly increasing positive force pulling from the center, but the cloud of inner electrons shielding the outer ones isn't really changing much?
Precisely. And that increasing positive pull it yanks those outer valence electrons closer and tighter to the nucleus.
Shrinking the whole atom.
It shrinks the whole atom. It goes from about 0.17 nanometers for sodium all the way down to 0.099 for chlorine. And that shrinkage is, it's the foundation for almost every other change we're about to talk about.
Okay, so if the change in the size of the neutral atom is dramatic, the change in ionic radii is even more complex. We have to compare cations and anions now.
We do. And if you look at the cations first, so that's your Na+, Mg2+, Al3+, they are all dramatically smaller than their parent atoms.
Right, because they lose that entire outer shell.
They've lost the whole third quantum shell. But even within that group of cations, the size still shrinks as you go from sodium to aluminium. That nuclear charge is still increasing, pulling those remaining electrons in the second shell even tighter.
And then we flip over to the other side, to the anions like P3-, S2-, and Cleo-.
And those are all larger than their neutral atoms. This time it's because you're adding electrons into the same outer shell, which, increases the electron repulsion. It forces the cloud to expand a bit.
But the trend still continues in a way, doesn't it?
It does, because the overarching factor is still that nuclear charge. So even among the anions, the size decreases from phosphorus down to chlorine. That rising nuclear charge starts to win out again, overriding some of those repulsive forces.
Now let's talk about structure and bonding. This is where we get that fascinating trend in melting point and electrical conductivity. If you actually plot this data, silicon just sits there on this massive, isolated peak.
That peak tells you instantly that something fundamental, something about the very structure, has changed. On the left, you have sodium, magnesium, and aluminium. They're all giant metallic structures.
And they have a clear trend themselves.
A very clear trend, a progressive increase in both melting point and conductivity. Think about aluminium. It's Al3+ in that sea of electrons. It's donating 3 valence electrons.
Compared to just 1 from sodium.
Right. So you get far stronger metallic bonding and way more delocalized electrons to carry charge. Higher melting point, better conductivity. It makes perfect sense.
Then you hit the outlier, silicon, 1683 Kelvin. The highest melting point in the entire period.
Silicon is a giant covalent structure. It's essentially this massive 3-dimensional lattice where every single atom is held by 4 incredibly strong covalent bonds.
So you need a huge amount of energy to break that network apart.
A massive amount, hence the huge melting point.
Mm.
And because it doesn't have any of those delocalized electrons, its conductivity just plummets. It's a semiconductor. It's the perfect physical bridge between the metals and the nonmetals.
And then after that peak, we fall off a cliff. The nonmetals, phosphorus, sulfur, chlorine, argon, their melting points are incredibly low.
Right, because for these, you're not breaking covalent bonds to melt them. They're all simple molecular structures, P4S8Cl2.
So you're only overcoming the weak intermolecular forces.
Exactly. Just those weak, instantaneous dipole-induced dipole forces. Now, what's interesting is that sulfur, with its S8 ring structure, is bigger and more complex than, say, the P4 molecule.
So its intermolecular forces are stronger.
A bit stronger, yes.
Yeah.
Which is why sulfur is a solid at room temperature, while chlorine is a gas. And of course, they're all terrible electrical conductors. They're insulators.
Okay, the final major physical trend to cover is the first ionization energy, the energy needed to remove that outermost electron. The general trend is a pretty sharp increase across the period.
Which makes perfect sense, right?
Yeah, the atoms are getting smaller, the nuclear charge is increasing, so that electron is being held much more tightly. It should be harder to remove.
It should be. But we have to look closely at the orbital configurations to really understand the 2 key dips in that graph.
Okay, the first drop, it's between magnesium in group 2 and aluminium in group 13.
Right. What's happening there is that aluminium is losing an electron from a porbital, which is just a slightly higher energy level than magnesium's sorbital.
So it's just a little bit easier to pull off.
It's marginally easier, yes. Enough to cause that noticeable dip against the overall trend.
And the second dip is between phosphorus group 15 and sulfur group 16.
This one's all about electron pairing. Phosphorus has this really stable, half-filled p subshell configuration. Very energy favorable.
1 electron in each porbital.
Exactly. But sulfur has 1 porbital with a paired set of electrons. And when you remove one of those, you're also relieving that electron repulsion within the pair.
So that repulsion gives you a little bit of a help, making it easier to remove.
It makes it slightly easier to remove, resulting in a lower ionization energy than you'd otherwise predict.
Let's use those physical traits. The smaller size, that increasing nuclear charge, as our bridge into their chemical behavior. How does this structural change affect how they react? Let's start with oxygen.
The reactivity really shows that smooth transition, doesn't it? From metals that are desperate to lose electrons to non-metals that want to share or gain them.
So sodium, magnesium, and aluminium.
They all react vigorously with oxygen. You get these bright, intense flames, and they form their respective oxides. Na2O, MgO, L2O3, they're all ionic solids.
And the nonmetals. Silicon reacts slowly to form silicon dioxide. Phosphorus, though, that's the spectacular one.
Oh, yeah. Burns vigorously, making those thick white fumes of P4O10. Then sulfur burns much more gently, with a little blue flame, forming that toxic sulfur dioxide, SO2.
Right, which can then be oxidized further.
It can, up to SO3. And we see this powerful shift numerically if we look at the maximum oxidation number that the period 3 element can achieve in its oxide.
Okay, so if we connect this to the bigger picture, the maximum oxidation number just steadily climbs. Sodium is +1.
Magnesium +2, aluminium +3, silicon +4.
All the way up to phosphorus +5, sulfur +6, and chlorine +7.
And that numerical climb is the definitive proof that the element is using all of its available valence electrons in bonding. It's a behavior that's dictated entirely by that rising electronegativity across the period. Oxygen is so electronegative, it forces all of them into these high positive oxidation states. It's a perfect yardstick for that metallic to non-metallic shift.
This rising oxidation state and the shift in bonding, it leads us directly to our next critical topic. Why does the reaction of these oxides with water change so dramatically? We go from making a strong base to a strong acid.
It's all about the bonding. So the first two, sodium oxide and magnesium oxide, are basic oxides. They have giant ionic structures.
Okay.
When sodium oxide dissolves, that oxide ion, the O2-, is a very powerful base. It rips a hydrogen ion, an H+, right off a water molecule.
Forming hydroxide ion.
Right, it forms 2 hydroxide ions, and that results in a highly alkaline solution. For sodium oxide, it's a pH of about 14.
And we use this practically, don't we? Magnesium oxide is the classic ingredient in antacids. Its basicity neutralizes stomach acid.
Exactly. But then we hit the transition point, and this is where the chemistry gets really sophisticated. Aluminium oxide, L2O3.
The amphoteric oxide.
Yes. It doesn't react with water, but it reacts with both acids, where it acts as a base,
Hmm.
and with concentrated alkalis, where it acts as an acid.
So it's not truly ionic anymore, even though aluminium is a metal. What's driving that dual nature?
This is a crucial concept. It's charge density and polarizing power. The aluminium ion, Al3+, is very small and has a really high positive charge,
A high charge
a
density.
very high charge density.
Yeah.
And this high positive charge strongly polarizes the big, fluffy electron cloud of the oxide ion next to it.
It distorts the electron cloud.
It pulls that electron density towards the aluminium nucleus, which reduces the pure ionic character of the bond and introduces a pretty significant degree of covalent character.
Hmm.
And that covalent nature is what allows it to react with a strong base, just like a nonmetal oxide would.
Wow, so that structural shift just sets the stage perfectly for the true acidic oxides. Silicon dioxide, phosphorus pentoxide, and the sulfur oxides.
Right. SO2 is giant covalent and insoluble, but we know it's acidic because it will react with hot, concentrated alkali. The rest are simple molecular. Now, the mechanism for their acidity is basically the reverse of what we saw with sodium oxide.
Okay.
Your nonmetal atoms, like sulfur or phosphorus, are highly electronegative. So when they bond to oxygen, they pull electron density away from the oxygen atom.
Which means when these oxides eventually react with water, the OH bond in the acid that they form is really weak.
Correct. That highly electronegative element makes the central EO bond very strong and the resulting OH bond in the acid very weak, so it readily gives up its H+ ion.
Creating a very acidic solution.
A very acidic solution. P4O10 reacts vigorously to form phosphoric V acid. SO3 forms sulfuric acid.
Yeah.
You get solutions with a pH of, 1 or 2. Very strong acids.
And we see that same structural divide when we look at the chlorides, right? Sodium chloride and magnesium chloride are our classic ionic chlorides. How do they behave in water?
They just dissolve. The polar water molecules surround and hydrate the separated ions. NaCl gives you a perfectly neutral solution, pH 7.
But magnesium chloride is a little different.
It is, and this is an important clue. For MgCl2, the solution is actually slightly acidic, around pH 6.5.
Why is that?
Well, that slight acidity is the very beginning of hydrolysis. The Mg2+ ion has a bit more polarizing power than Na+, just enough to slightly react with the water molecules around it, releasing tiny amounts of H+.
So MgCl2 is the perfect setup for the really dramatic behavior of the covalent chlorides, starting with aluminium chloride.
Indeed. Aluminium chloride Al2Cl6 is covalent. So when it dissolves, that highly charged Al3+ ion, again because of its high charge density, reacts strongly with the water molecules. It literally strips them of H+ ions.
That's hydrolysis.
That's hydrolysis, and it makes the solution quite acidic, typically a pH of 3.
And then the non-metal covalent chlorides, AgCl4 and PCl5, are the most violent of all.
They hydrolyze immediately and rapidly. You see these visible white fumes of hydrogen chloride gas, HCl, just pouring off instantly.
Leaving behind a highly acidic solution.
Extremely acidic, pH of 2 or so. And for silicon chloride, you also get a white precipitate of silicon dioxide, SiO2, forming in the water. That extreme reactivity just highlights their purely covalent, simple molecular nature.
Okay, so the ultimate test of understanding all this is being able to deduce an element's position just from its properties. Let's try to integrate all these facts.
Let's do it. Imagine you have an unknown period 3 element. You're told its chloride is a liquid, and it reacts violently with water, giving off white fumes and an acidic solution.
Okay, that right there tells me it has to be a covalent chloride, so it's on the right-hand side, probably silicon or phosphorus.
Good. Now, what if we analyze its oxide? We find it has a very, very high melting point, but when we test it, it does not react with alkali, unlike the amphoteric Al2O3.
The high melting point screams giant covalent structure, and the fact it doesn't react with alkali means it's insoluble, which leads us straight to SO2.
Exactly. So we can confidently deduce the element is silicon. In group 14, we've just integrated structure, conductivity, reactivity, and acid-base behavior to solve the puzzle.
So what does this all mean for you listening? The entire narrative of period 3 is this change from strong ionic bonding over to an increasing covalent character. And it's a shift driven entirely by that increasing nuclear charge.
And the resulting high charge density and polarizing power of the ions.
Right. And that progression creates everything from basic compounds like antacids to some of the strongest acids we know.
Here's a final provocative thought for you to take away. We know period 3 pretty well now. So consider an element in period 5, group 15, so that's directly below phosphorus. Based on what you know about group trends like size, increasing down a group and period trends, What properties would you confidently predict for its melting point and the acidity of its highest oxide? Would it be more metallic or maybe less acidic than phosphorus?
That's a great application question using both axes of the periodic table. We've covered everything from physical size to complex hydrolysis reactions. Thank you so much for joining us as we explored the fascinating and very predictable patterns of period 3.